We are in chapter 4 now. Before I move on talking something about chapter 4, let me tell all of you that you guys have done very good in the exam as well as in the homework and going over the practice problems. I thank you for your hard work, and overall the view on the exam and homework looks good, so you don't have to worry about. But I would say you should better look for your lab grades. I really don't know. There are a couple of professors teaching 111 labs, so I don't know who will be in your lab instructor. You can double check in the schedule. Okay, right now we are in chapter 4, where we have to start with Newton's law of motion. In the beginning, you got to understand that the force and mass, the difference between force and mass. Force are push and pull, and mass is similar to force, which is a scalar quantity. In section 2, the Newton's first law of motion says that an object in the state of rest or in motion, will be at rest or will be at motion. Motion, I mean constant velocity, unless some external force is applied to change the position or change the motion of the object. Well, next page we are here now to define what's inertia. Inertia actually a normal tendency to retain at rest or in motion with a constant velocity. The mass of an object is a quantitative measure of mass, and the quantitative measure is measured in kilograms, grams and slug. Kilograms for SI unit, grams for CGS, and B slug. The internal frame, which is in Newton's law of motion, is valid. That's what it is in figure. You should refer to figure 4.3, page number 81. Now this table is showing you here mostly the units which I mentioned to you now. Now we're moving to the Newton's second law of motion. Where an external force or a bunch of forces acting on an object with a mass m and acceleration a, that results in directly proportional to the net force and has a magnitude which is inversely proportional to the mass of the direction of acceleration is same as the direction of the net force. So we can derive with an equation now. Look at this. We have acceleration equals sum of all the forces divided by mass, or sum of all forces equals mass times acceleration. The unit for the force here is defined to be kilogram times meters per second square, and that's in newtons. All the force is unit wise called newton, and newton is 1 newton equals 1 kilogram times meters per second square, which is mass times acceleration. In CGS it is dyne, in BE it is pounds. So you can go over example 1 on page 83. Now we're going to see what happens to a force when we resolve into the components, like x component and y component. And you guys know so far that the component can be resolved with an angle, right? That was in chapter 2. But now we'll be resolving the forces here with mass and acceleration, because second law says force equals mass and acceleration. So if you have a force F, as you see in this figure here, then you see sum of Fx will be mass times Ax. That means whatever the mass is, you multiply times acceleration in the direction of x. Okay, let's say you have bunch of forces, so individually you have to add them all to make the total in the direction of x, similar to what you did in the component method of adding in first chapter. Now Fy again is mass times acceleration in the direction of y, as you see in this figure here. So you have components now for F, like Fx, Fy. Component of acceleration is Ax and Ay. This is very typical how you apply that in the problem. You can go to example 2, page 84. It's not hard to understand. You should read at least 1 or 2 times to get into it. This is a better figure, I would say, which I took it from the textbook. Look at this one right here, okay, which I showed you before, and it's showing you part by part how the Fx, Fy is defined. Now we are at Newton's third law of motion, okay, which is section 4.4. Okay, when an object exerts a force on a second object, the second object will definitely oppose it, and it will oppositely will apply a force of same magnitude on the first object. That means, in a simple word, I would say for every action there is a reaction. So that's what I would say rather than a hard definition. So you can go to figure 4.7, page 85, where he is showing you P in one direction, P in other direction, and positive and negative. Alright, now we have to define what is gravitational force. It's in gravity, or the force due to what? We have all these planets, they are attracted each other with gravitational forces. So Newton's law of universal gravitation says, you can see that in 4.9, where you have force is equal to g times m1 times m2 divided by r square, where g is a gravitational constant, m1 is an object, and m2 is another object. They are sitting at a distance r, as you see here. Okay, due to attraction, they will come slowly and slowly to each other, okay, depending on the distance. And the gravitational force is defined to be here, one positive, other is negative, as you see in this. I have a neat picture which is very much clear. You can look at this. Same thing which I draw myself, but this is a better picture for you guys to understand. Now look at this. The gravitational constant here is G, okay, which is 6.674 10 to the power 11. This number is very important number to solve problems when you will be doing some practice problems. You can, before that, you can go over certain examples worked out in your book also, but I'll definitely give you, as I gave some problem for practice before the exam. This is another example where in space we have Moon and Earth with a distance r, and similarly one positive, one force negative, they attract each other here, okay. And the same thing is shown in a line diagram, and we will be using the gravitational force equation to find out the force. Another important thing to know is what's the difference between mass and weight. We say he weighs 120 pounds, but I would say, well, what that means? Because the weight of an object or a body is on and above the earth is the gravitational force that exert the earth on that object. So there will be external force acting on that object, and that is due to the earth. And the weight always acts downwards towards the center of the earth. The unit of weight is in newtons, like force. Okay, so W is weight here, which is force due to that gravitational equation we had. Now we have G times m1 m2 over r square, where the capital M is the mass of earth, r is the radius of the earth, and the mass of the object is small m. Okay, so you can go to figure 411 on page 89. Now we're looking for the relationship between mass and weight. We again use the same equation what we had in the previous page I showed you, using the equation W equals G times me over r square times mass of the object. From there we can simplify further. W is the weight. See, G is a constant here, okay, and me is also constant, r is constant, all three are constant, right? So I would say, as they are all constant, we can put them together and write down small g, where g is acceleration due to gravity, which we talked about in free fall in chapter 2. So we define now that g is always a constant, okay, and g will be equal to capital G me over r square. R is the radius of the earth. So mass is a quantitative measure of inertia, don't forget it, that's very important to remember. Now we'll talk about what a normal force is. Normal force, as the name itself, acts 90 degree or normal to the surface. So normal force is the component of the force that is on the surface on the object which is in contact and is perpendicular to the surface. So you can go over the figure number 4.3, page 91. The other example is also there. Before I move on to the next page, I would say sometimes if there is no external force, right, on that object, then the weight will be the normal force, because as you know, unit of weight is in newtons. So look at this figure here. Okay, here you have the normal force acting upwards, weight is acting downwards, so they balance each other. That means the weight is equal to the normal force. See that? Now the two forces act on this block, and with the velocity not there, it's zero, no velocity, no acceleration. Okay, so weight W and normal force are balancing each other. Otherwise, if they don't balance, then it moves somewhere, either in direction of x or in direction of y. That's what I will show you in the next equation, where we will find how the equilibrium of forces takes place and what is the condition. Okay, before we go to that last topic, we have two different types of frictional forces, as you see. One is static friction, other is kinetic friction. Static friction is no motion, it's just standing somewhere, but there is still friction. Kinetic friction is when the object moves from one point to the other point. So previously you saw the normal force is acting on this object. When the object moves, the component of the force parallel to the surface is called as frictional force, or just simply friction. Okay, so this the object is sitting on a surface, and we can always say, okay, that is not moving, still there is friction due to the surface, and that is known as static friction. Now look at this. People always confuse that friction means the object should move or the person standing should move. How come there is a friction if somebody is not moving or the object is not moving? Alright. Now the coefficient of static friction is mu s. You can refer to figure 420 on page 95. This is the constant of proportionality, where you have the frictional force Fs max equals to mu s times normal force. So frictional force is a part of the normal force, is a component. It can go maximum from 0 to max value depending on the situation, depending on the problem you solve rather. So the normal force, it plays an important role in static friction. The magnitude of static friction, okay, Fs, can be a value from 0 to Fs max. Go over the example 9 in page 97. Alright, now we're going to kinetic friction. When the two surfaces begin sliding with each another, that means they are in motion. This type of friction is known as kinetic friction. This is in very simple words. There are too many complicated um, statement in your book. You don't have to worry about that. Just simply understand when there is motion, there is kinetic friction. But there is always a friction there, which is similar to the static friction, where mu s max was there, not max. I mean, sorry, force was maximum at that point because it's now moving. But here it is a variable force, so the Fk, which is the coefficient of kinetic friction, equals, I mean this is kinetic force, I'm sorry, it's kinetic force, and here you have mu k times Fn, the normal force again. So you can go over example 4.8, page 97. To tell you about kinetic or static friction, the problems are very simple. You see, in these equations you have the force for kinetic friction, this is the mu coefficient, this is the normal force. Out of the three variables, two will be given to you, and you solve and figure out the third one. They are very simple problems, as a matter of fact. Alright, now let's move on to table number 4.2, where 4.2 is used for mostly solving the problems. You have all the data for mu s and mu k. The last topic we have here is the equilibrium, how it takes place when a bunch of forces acting on an object. From Newton's law of motion we'll derive that, which is on page 101. Then object is in equilibrium. An object is said to be in equilibrium when it has zero acceleration. Zero acceleration means it's not moving nowhere. And sum of x component and y component has to be zero. Again, mind you, x component, if it is not zero, then it will move in the direction of x. All the forces, let's say, are resolved, and there is some value for x component, then the object will move towards x direction. The same thing happens if sum of all the y components are not zero, then it will go up or down. Okay, so the condition for equilibrium is both fx, sum of all the x component, sum of the all y component, has to be zero. Okay, that ends chapter 4. I would request all of you, please limit yourself to the sections we are covering now, and you can also simplify the definitions in your own way, the way you understand, or you can understand the book language. It's very fine. So that's how you should practice more and more. There is enough time for one chapter for 1 week. Okay, so I don't think that will be difficult. I understand some of you work in day and night. It's a very bad time now, and we all share with that, and I hope you will do the best you can, and I'll be helping you the best I could. Thank you. Have a good night.